Yeah, we completed the moment of inertia concept. Yes. Yes, yes. Then we have to come to the another concept here, which is linked to moment of inertia. Okay. That is what we are going to discuss today. Is nothing but torque. Okay. Yeah, we are entering into pure rotatory motion, which are linked to moment of inertia. Who is this torque and how to calculate it? Okay. Come to here. How to calculate the torque? Suppose you consider this is a door, and usually with the hinges, the door is fixed to the frame somewhere here with the hinges. Okay. Then they fix one handle somewhere here. This is the handle, right? And to open the door or to close the door, we apply some force on the handle. Okay. That is, we push perpendicular to the door, we apply some force. Perpendicular, I can't draw. Okay. That's why just I put one arrow mark here like this. Yes, that only Nana. Push or pull, anyone. Okay. Yes, actually. This is the force what you are applying. And here, this is the axis. From axis, at what perpendicular distance you apply the force. Okay. Actually, this is the distance where the handle is fixed from the axis. Okay. This is suppose R. Then the product of force to perpendicular distance from the axis to the force. Okay. So here torque is defined as the product of force applied to the perpendicular distance. Good morning. To the perpendicular distance from the axis. Okay. That is represented usually with the letter tau, like this. That's why I started here tau torque. Okay. That torque, here we write it as tau is equals to force F into perpendicular distance. Okay. Yeah, this is the formula. And here, yes, correct, Dipali. That torque is a vector. That's why I write it in the vector form as tau bar is equals to get the vector here, these two are vectors now. These two are vectors means we have to take the dot product or cross product to get the vector on the other side. Cross product. Yes, correct, Amol. Yes. So cross product, that one we have to take it as R bar, the position vector, cross force bar. Don't take F cross R. If you take cross product in reverse, then you will get the negative sign. I think all of you know, not the dot product. Okay, Arudra. It is cross product. Dot product gives a scalar. Okay, right. R cross F. Here, problem is if you apply the force perpendicular to the door, exactly whatever the value given there on the board is the perpendicular distance. But if you hold the handle making some angle, if you apply the force, then the given R is not the perpendicular distance. Then I have to drop a perpendicular from there to here, from axis to the force, line of action of force. From force to the axis, if you drop a perpendicular like this perpendicular will be the perpendicular distance. So take care. Whether the line of action of force and given R are perpendicular, happily we take the product of those two. If the line of action of force makes some angle with the R from axis, then we have to take the perpendicular distance here like this, red color separately. It is the perpendicular distance. Okay. In this case, if you see here, what will be the angle between these two? F inwards like this, or measured from there, both make an angle theta here. In mathematics, opposite angle it is also theta. Then look at this right angle triangle. In this right angle triangle, opposite to the right angle, it is the hypotenuse. That's why here, if you use to get the perpendicular distance sine theta, then you will get sine theta is equals to, yes, opposite, correct, perpendicular, opposite side, perpendicular distance by hypotenuse. Hypotenuse is R. Therefore, perpendicular distance, you are getting R sine theta. Okay, that equals to R sine theta. Now you can substitute over here in place of torque. Yes. Yes. According to right hand thumb rule only. Lakshmi Gayatri. Okay. Then Deepali, we are writing the mod of the magnitude of torque is equals to R cross F. That is, magnitude is F into perpendicular distance is R sine theta. Okay, this is the torque. I think now I am able to recollect something here. I explained this torque concept in vectors chapter in the very beginning for the examples of cross product and dot product. Am I right? Yes, correct. This one already you know, I think you are right. Exactly. Okay, this is the torque today we are going to discuss. Okay, here in detail. Then it is a vector and its units, if you ask, directly you can say, what are the units from the formula? Force into perpendicular distance means force is Newton. Yeah, correct. Newton per meter, Adipali, or into meter? Into perpendicular distance. Joule, correct. But we should not use the joule. Why? Because joule we use in dot product. Okay. That's why here in cross product, we take it as like Newton into meter. Exactly. Don't write it as joule. No other name, no other name. Just Newton into meter. That's it. And CGS, you know, that is dyne centimeter, dyne into centimeter. Don't say ergs. Both are equal to joule and equal to earth, but we are not represented with those units. Just they are trying to distinguish the cross and dot products. Dot product values we measure in joules. Cross product values, same thing, we are measuring in Newton meter. Now got the clarity, Lakshmi Gayatri? Okay. Yes, yes. Just to distinguish whether it is coming from cross product or dot product. We are simply leaving it like Newton into meter, even though it is equals to joule. Okay. This is simple torque concept, Nana. Right? Then if you see this formula, in what way it is related to our moment of inertia? Where is the moment of inertia here to find out the torque? Why Sir said moment of inertia is the heart of this chapter, interlinked to all. Where is the interlink? Okay, you may set somewhere here. You won't find anything here. Okay. Then what I say, if you come through another physical quantity, you will get the clarity over there. What is the another one, sir? Like force, how we got from linear momentum. Here torque, you try to get from angular momentum. Okay, means rotational momentum. Their linear momentum, product of mass to velocity. I think I'm not confusing you all. You are able to understand. Linear momentum is product of mass to velocity. Same momentum in rotatory motion by virtue of its angular velocity. Yes, yes, thank you. By virtue of angular velocity. The physical quantity that you will get here is the angular momentum. Okay, that angular momentum we represent with the letter L, and here it is exactly identical to the linear momentum. It is defined as the angular momentum is the product of momentum, linear momentum, okay, to the perpendicular distance. Oh, every physical quantity we are getting the product of perpendicular distance from axis, sir? Yes. Instead of force, if you take here momentum, momentum into perpendicular distance is angular momentum. Okay, how you write it, sir? Okay, come to the formula. Angular momentum L is equals to linear momentum P into the perpendicular distance. Oh, exactly identical to it. Oh, similar to this formula, sir. Yes, similar to this formula. Angular momentum is equals to linear momentum into perpendicular distance. Oh, I understood one thing, sir. Their force vector, perpendicular distance is a vector, so immediately you took the cross product. Even here also, I know linear momentum is a vector, perpendicular distance is a vector. I think you are going to take the cross product again. Am I right, sir? Yes, thumbs up. You are right. 100% correct. Okay. Yes. So vector form. This is also a vector. I write here. L bar equals to. This is equals to R bar cross linear momentum P bar. Okay. So here no need to again find out the perpendicular distance. In the previous diagram already we calculated that perpendicular distance is R sine theta from axis. So straight away I write mod of L bar, its magnitude. that is equals to P into perpendicular distance is r sine theta straight away. Okay, and again here if you ask what are the units, directly I write here units, linear momentum, kg meter per second, mass into velocity, into perpendicular distance into meter, means kg meter square per second. Understood, Nana? The unit, how we got? Yes, okay. And CGS, I think, thank you. CGS, I think, here, gram centimeter square per second. Okay, good. Good morning, Nana. I think you joined in YouTube. Okay, right, no problem. Gram centimeter square per second. Yes, I understood. Okay, then come back to conversions. We forgot, Nana, writing here. 1 Newton meter equals to how many dyne centimeters? Okay, so conversions of both the units, SI to CGS. 1 Newton meter, it is exactly equals to joule. Yeah. 10 power 5, Anna, Ishan. 1 joule is equals to how many earths? Not Newton. One, now it is correct, Ishan. Little bit, I think, hangover yesterday. Am I right? No. Thank. Okay, right. Then one. No, Nana. That is Newton per meter, Deepali. Every time I think you are taking wrong, Nana. Newton into meter, kada. Okay, right. Yeah. Good. Getting some Newton into meter, Nana, not Newton per meter. Yes, holy Mr. Manikanta, you're right. Okay. Right. And here, this is 1 kg meter square per second. If you see here, this one, anybody will say gram centimeter square per second. What you forget? Ten into 10. Sure. Oh, Manikanta, what is this? Yes, Amo, you are right. Once you check, oh, 10 for 10. Kg is it? Yes. 10 power 3 grams. Meter is 100 centimeter. So 10 square centimeter whole square. Meter square. This is 10 power 3 grams. Second, there is no change here. Second and second. So 10 power 3 and 10 power 4 all together you are getting 10 power 7. Same thing you are getting there. Yeah. Okay. Right. To remember easily, I wrote both the conversions. Same, sir. Yes, correct. That's why I wrote here combined. You can easily remember. Both are 10 power 7, 10 power 7 conversions. Okay. Good. These are the conversions of units in numericals we try to use whenever required. And then here I understood, I think you are eagerly waiting there to find out the relation with the heart. That is moment of inertia. Okay. Now he is saying this angular momentum, while writing the cross product anywhere, R cross, write it as moment of, not movement, moment of. This is cross product of linear momentum. That's why moment of linear momentum. Is defined as angular momentum. Simple definition for angular momentum. No need to write this big one. Product of momentum to the perpendicular distance. Just moment of linear momentum. That's it. And number 2 here, same thing we got even in torque also. That is R cross F. Yes, same here. Moment of, not linear momentum, moment of. This is identify the definition of torques, short definition. Moment of, what to write here? Force, I think. Moment of force. Am I right? Yes, yes. Moment of force is defined as torque. This is simple definition for torque. Okay. So this is moment of linear momentum, that is moment of force. So both are interlinked to moment of. So there will be some relation between the two. Okay. That relation he is saying here. The relation between torque, sure, I will rewind, torque and angular momentum is, yes, Lakshmi Gayatri, this is the previous page. Okay. Right. The relation between torque and angular momentum, he is saying, simple. Shall I write F is equals to here rate of change of linear momentum, the original definition from Newton's laws. Okay. Same thing, I am taking product of R on both sides. Okay. That is F into the perpendicular distance here. There d by dt of P, that side also I am multiplying into perpendicular distance. Then I think you can interrelate these two, Nana. Okay. Force into perpendicular distance is a torque is equals to d by dt of P into perpendicular distance, you know it. That is angular momentum. So tau is equals to dl by dt. We got one formula here, the relation between torque and angular momentum. Okay, now you understood this one, how I wrote tau and dl by dt. Yes, just from here, since f is equals, sorry, f equals to df by dt, from there, just I wrote from here. Yes. Okay, this is just a reference. Okay, right. Come back to here. Torque and angular momentum, I interrelated. Okay, and then here that one, even if you want to write in vector form also you can write, or tau bar is equals to d by dt of el bar. Okay, sir, still I am not getting whatever you are saying. Simply you are extending the concepts, sir, here, but not disclosing how they are interrelated to the angular momentum concept, sorry, moment of inertia concept. Yes, I understood your pain. Wait, now you will get. How, sir? Look at L of a point mass in rotatory motion. Rotatory motion is continuously moving. It has some linear momentum, perpendicular distance we can calculate. That one with is equals to perpendicular distance into, here I write the linear momentum. Okay. That perpendicular distance we represent with the r. Suppose theta is 90 degrees, r into p I write. If theta equals to 90 degrees between them, okay, that I write it as mass into velocity. Okay, that I write it as r into m into here in rotatory motion. Anyone remember V is equals to the r omega? Remember this formula? In rotated motion, V equals to r omega. Yes, Ishan, thank you. Right. Then here you observe, you are going to almost getting how to interlate. M into r square into omega. Look at who is this mr square. Who is this mr square for point mass? Yes, exactly. Moment of inertia. That's it. Yeah, you are getting now. Yeah. Thank you, Nana. Thank you. That implies here L is equals to mr square into omega. V is equals to r omega. Exactly. You are right. Okay. Yes. Then come back to here. L equals to mr square. I write it here as I into omega. Now you see the two physical quantities today we discussed. One already interlinked with the heart, moment of inertia, the formula. Okay, that one you can write even vector form also. Or here I write this L bar equals to moment of inertia is a scalar. I think all of you remember. So I into omega, I write it as omega is a vector. I think all of you remember. I into omega bar. Don't put any dot or cross here. Why? Because it is a scalar. It is simple multiplication with a scalar. Okay. L bar equals to I into omega bar. One, what you asked, I gave here. And second one, you are again waiting here. How that other physical quantity today I discussed, angular momentum interlinked to, torque interlinked to moment of inertia. Okay, yes, tau is equals to what I said, d by dt of L naught, just now I said. Okay, then d by dt of L, now you write the new formula what I wrote in the above one point, I into omega bar, then tau bar equals to I write I, moment of inertia. Yes. Yeah, I into d by dt of omega. Anyone remember? Yes, alpha, Srestha. Wow, right, good. Amo, good. Tau bar equals to I into d omega bar by dt is alpha. Meher, correct. I alpha bar. Okay, this is the another one. Scalar form also, yes. Angular acceleration, exactly, Rachmi Gayatri. Tau magnitude is equals to I alpha, simply. Okay, this is another formula what we get. Okay, see here, everything is interrelated to moment of inertia. That's why first here we discuss the moment of inertia. Now check over there, Nana. If you don't remember the moment of inertia formula for a particular body, you can't calculate the torque, you can't calculate the angular momentum. That's what I told. That table is very important. If you don't buttify, simple, leave this chapter. Okay, simple, come out of this chapter. If you don't know about that table, moments of inertia of different bodies. Okay, So the table is very important. Yes, 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 very good, Shyam. Right. Yeah, good, good, Deepali. So I think again all of you revised the table. Okay. So I think you are good enough in the moments of inertia. Yes, yes, thank you, Nana, thank you. Okay, good. So here I'm coming to while interlinking this concept with the torque and angular momentum, what the kind of models you get. Okay, once we check, first we come to here. Suppose better I write number one, otherwise you may feel it as moment of inertia, modal moment of inertia. No, it is not modal moment of inertia, it is modal number one. This is just number. Okay, right. Model number one here is when a body is moving, or in this chapter we have to say rotating, not moving, is rotating with uniform angular acceleration. Uniform angular acceleration. Just like what I'm saying, uniform angular velocity, sorry, uniform uh, acceleration. Okay, their uniform acceleration, here uniform angular acceleration. Then try to recollect, there you wrote 4 equations of motion. One is V equals to like U plus AT, I think all of you remember. S is equals to UT plus half AT square. V square minus U square, yes, 2AS. And Sn equals to distance traveled in the nth second, U plus A by 2 into 2n minus 1. Okay, I think all of you remember. Same type of equations. Actually, we said these equations of motion when a body is moving with uniform velocity or uniform acceleration. Uniform acceleration, remember, uniform acceleration. If a body is moving with uniform velocity, simple use V is equals to S by T. So S is equals to Vt is used only when the body is moving with uniform velocity or uniform acceleration. No acceleration. Lakshmi Gayatri finally understood. Is used only when the body is moving with uniform velocity. That is no acceleration. Yes, correct. Uniform velocity. Right, correct. Good. And don't use this formula when a body is moving with uniform acceleration. In bracket, A equals to 0. Very good. Same type of equation. Here also we have to write. When a body is uniformly accelerating, means with uniform angular acceleration. Okay. Actually, we say alpha equals to d omega by dt. Na? Formula. That implies omega equals to, shall I take integral, that is d omega, integral d omega equals to integral alpha dt. That implies omega within the limits, starting with omega naught to omega, is equals to, in uniform angular acceleration, alpha is constant taken out, integral dt, that is alpha t, in the limits 0 to t, that is alpha t. Here we will get omega minus omega naught. That implies omega equals to, you will get omega naught plus alpha t. These kind of equations previously given in my class, no? Equations of motion. No. Oh, first time we are seeing. Yes or no? Manikanta says everything yes. What, Manibabu? Yes or no? Simple, Nana. Alpha is equals to, I wrote in differential form, na. Not even. For that, yes. Okay, right. Alpha is equals to d omega by dt. D omega is equals to alpha dt. Na. That's why I took the integration. I wrote differential form, na. That's why integrated. Even though here I did not integrate the alpha, Nana. Since it is constant, it is taken out. Okay, just a dt I integrated. That's it. Now you understood? To extract the formula. What happened, Lakshmi Gayatri? Why you did not follow? Here, what is the problem in my derivation? I think you got some. Yes, okay. I think you got some doubt here. I don't know. You went into a misconcept. Integration is used only when it is in non-uniform motion. Otherwise, don't use the integration. Yes, yes, yes. Okay, integration is the universal method. Anywhere you can use. If it is constant, simply take it out. Otherwise, substitute the value and integrate. Okay, good. So such type of equations exactly identical to here. Like in place of V, I got omega. In place of U, I got omega naught. In place of A, I got alpha. Okay. How you get, sir? Simple. In a short way, try to understand from here. V is equals to R omega na. U, that is also velocity. You write it as R omega naught. Initial velocity, initial angular velocity. Plus alpha. Okay, sorry, A. A is equals to R alpha relation into T. Are you comfortable with this method, Nano? Yes. Are you comfortable? Yes, yes. Okay. Then why I'm writing here? To avoid the integration, in a simple way, I'm going to get the same equation here by taking R out from both and cancelling on both sides. I will get omega equals to what? Thank you, thank you, thank you. Very comfortable. Thank you. Omega is equals to omega naught plus, both are same only, both are same only, but it is a simpler method. Omega is equals to omega naught plus alpha t after cancelling R. Okay. So every time no need to go to integration, provided if it is moving with the uniform angular acceleration. So this thing what Lakshmi Gayatri asked, sir, why you are using the integration? Yes, for her sake, I am avoiding that integration and directly I am going to here omega is equals to omega naught plus alpha t, or in the third method you can do in another way as uniform angular acceleration alpha is equals to d omega by dt means if alpha is constant, we can write it as delta omega by time. That is omega minus omega naught by time. That implies alpha t equals to omega minus omega naught. That implies omega is equals to omega naught plus alpha t. Method 1, method 2, method 3. In 3 ways I explained, or this is the third method. Now, is it crystal clear or not? Yes. Crystal clear. Yes, correct. Crystal clear. Very good. Right. So here the other formulae, I am not deriving none. Okay. Simple. Yes. Thank you. Thank you. Thank you. Right. Very good. Not getting, what happened? The top end you are not getting there. Oh, other part. No, no, all of you not getting the full board. Yes, all are getting the full board. No, no. Why you are not getting the full board? I think you have to adjust in your. Ah, now it is clear. Okay, then no problem. No problem. Then okay, okay. Ah, right, right, right. Okay, good. Right. So omega is equals to, we are getting omega naught plus alpha. Right. So first equation that implies, here I write, from the three Altier methods, okay, the equations, yes, yes, maybe some glitch in the YouTube, you are right. From the three Altier methods, the equations can be written similarly as first equation, omega is equals to omega naught plus alpha t, I write. Second equation also you can write, try to recollect, S is equals to r theta from sector principle long back I gave in circular motion. U we already wrote here in the third short method, r omega naught plus a half alpha already we wrote here, sorry, A we already wrote here as r alpha into t square. From this, I think again if you take r out and cancel on both sides, you will get the second equation as theta is equals to, sorry, I forgot here writing t, ut. So omega naught into t plus half alpha t square nana. Second equation straight away right here, theta is equals to omega naught t plus half alpha t square. Any problem? Yes, Akhil, correct. That only I'm not writing here. That only I'm writing here. No problem at all. Okay, very good. This is the second one, what we got here. Okay, yes. Now third one, without my help, will you say? B square minus U square is equal to 2. Wow, Akhil, good. In place of V, you will get R omega, means omega square. Very good. And in place of U, you will get R omega naught, means omega naught square equals to 2. A, in place A, in place of A, you will get R alpha, that is alpha. And in place of S, you will get R theta, that is theta. So understood the third one, how we got omega square minus omega naught square is equals to 2 alpha theta. Yes, very good. Now fourth one will be damn easy. Now why? Because already you understood the yes amount. First three. Last one writing very easy. Sn, simple, without explanation I am writing here. Theta n. U directly omega naught plus A directly alpha by 2 into 2n minus 1. That's it. Yeah, thank you. Thank you. Thank you. Right. So here finally we got 4 equations of motion for the body moving with the uniform acceleration. Yes. Okay. These equations we use to find out the alpha. For what purpose, sir? After finding out the alpha, we try to find out the torque. Means these equations are helping us to find out the torque. Intermediate, we are finding out alpha in the middle. Okay, we find the alpha, then we find the torque. That's why they are helping to find out the torque. Okay, good. So understood here, Nana, 4 equations of motion. Yes, good. Right. How to use these 4 equations and how to find the torque, tomorrow we will discuss in the class. Okay. Yes, next class. Very good. Right. Okay. So do you want the pages, Nana? If you want, you can take. Otherwise,